Hello everybody. This is our last video for the section where we discuss critical points and optimization problems. So let's go ahead and review solution to example 6, where we have a polynomial of two variables and we would like to find the absolute max and min values of the function on the given region D. So here you see that this polynomial is a little bit more involved than the functions that we've seen so far. And it is not as easy to visualize as something like x squared plus y squared, right? Because it is not going to be symmetric about the origin. And also, in addition to that, we have D that is a rectangle that's not centered at the origin either. Okay, so that means for this problem, I will be analyzing the behavior of the function on each one of those sides of the rectangle that I labeled with L1, L2, L3, and L4. Okay, so this picture right here on the left, it is just the representation of our region D. X is between 0 and 4, y is between 0 and 2. So we would like to look at the behavior of our function over this rectangle, right? So on the interior part and also on the boundary of the rectangle. Okay, so the first part is the same as before. We compute the partials of our function, set them equal to 0, and solve this linear system, finding critical points, and we're going to see if these points are inside the region. Okay, so you can see that the derivatives are fairly straightforward to compute. Once we simplify and combine like terms, do some reduction by constants, we get this system right here. And at this point, the easiest thing to do is to eliminate the variable x. So if you add these two equations, then we're going to get 3y is equal to 3. And from here, y is equal to 1. And then by back substitution, we find that x is equal to 3. Okay, so we have one critical point, 3, 1. And this point is on the interior of our region D. So let's go ahead and mark it. So let's say this is 3 and 1 over here. So that's the point that we determine in the first portion of this problem. Okay, so we have done this before, but now we need to analyze the behavior of this function on each of these line segments. So how are we going to do that? All right, so let's start with L1. And let's see what happens here. Okay, on L1, notice that y here is 0. Okay, so I can relabel y is equal to 0 and relabel my variable x as a parameter t. So x is the one that varies, and it varies from 0 to 4. So I'm going to set range for my parameter t to be from 0 to 4. Okay, once I do this, we can substitute y is equal to 0 and relabel x as t. So we're going to plug in this in here, and this is our original function. So we're rewriting f in terms of x and y as a new representation, just a function of one variable t. Okay, and you'll see why. So once we plug that in, combine like terms, we get a polynomial, a quadratic polynomial in terms of t. And here we can compute the derivative of this polynomial in order to determine the critical point. Okay, so that's what we've done in Calculus 1 when we were working with a function of x, right? So we find the derivative, set it equal to 0, and solve. In this case, we're solving it for t. So t is equal to 2. That's where we have a critical point. So we first point right here, a with coordinates to 0. And because this is a polynomial that's opening up, we know that that's going to be our local minimum. Okay, so let's go ahead and mark it. I'm going to mark it on my graph. So 2, 0. So let's say over here we have our point A. Okay, and now we're not going to discuss local maxima just yet, because you will see that these points will kind of coincide with all of the lines, right? So you'll see what I mean, and you probably have your intuition telling you, yeah, we should definitely consider the corners of that rectangle. Okay, so I'll come back to that portion of the solution once I discuss every line. All right, so L1 is done. Let's mark it as it's done. Okay, that's where we have a local minimum. Okay, now we do the same type of analysis for L2. So what happens on L2? That is where x is fixed. So here we have x is equal to 4. Okay, so we're going to substitute 4 for x. We relabel y as the variable t, and now that varies between 0 and 2. Okay, we do our substitution. Okay, so this used to be f of xy. Now it is a function of t only. Okay, we once again get a polynomial of second degree in one variable. That's our polynomial. We're going to compute its derivative, set that equal to 0, and solve for t. Okay, and that's exactly how we done this type of problem in Calculus 1. So this is t is equal to 5 over 4. And what is the next point that we get? Remember, x was fixed, that is 4. So y is the one with coordinate 5 over 4. Okay. All right, let's go ahead and mark that point on our graph. Let me scroll back up here a little bit. So x is 4 and y is 1 1/4. So let's say roughly over here. That's our point B. And again, we know that the behavior of this polynomial, the general behavior, okay, it's a parabola opening up. So that point is going to be a local minimum. Okay. All right. So this portion is done. Let's keep going with L3. Let's take a look at what happens at with L3. L3, what is fixed? Y is fixed and it's equal to 2. X is the one that varies between 0 and 4. Okay, so let's take a look at the solution. So y is 2, x is the variable between 0 and 4. Same idea. I'm going to let you verify that once you plug in those substitutions, we get a parabola. Okay, we get a quadratic function here in terms of t. And once we differentiate it and set that equal to 0, solve for t, we get t is equal to 4. So our next point is 4, 2. Okay, so 4, 2, where is that point? Let me return over here. 4, 2 is one of the corners, right? So 4, 2 is this point right here. That is point, what do we call it? Call it C, right? Okay. All right. So now the last thing we need to do is take a look at L4. This is where x is equal to 0 and y varies. Okay. So x is 0, y is the variable, and it varies between 0 and 2. We plug in those substitutions. We get another parabola. Okay. And this parabola also opens up. We differentiate it, set that equal to 0, solve for t. T turns out to be 1/4. So our last point is 0, 1/4. And let me go ahead and mark it on our graph. So 0, 1/4, somewhere here, roughly. Okay, let's call it point D. All right. So that's where we have local minima. Okay, so now let's take a look at all of these curves. I circled all of these functions. Let me go ahead and circle the last one. So that would be this one right here. Okay, all of these functions are quadratic with a positive leading coefficient, right? Okay, the coefficient that goes with t squared. All of these functions have a graph where the parabola opens up, and that's why all of these points in the box A, B, C, and D, that's where we have a local minimum. Okay, and you can see that what we need to do now is investigate the behavior of our function at the corners, because that's where we will have local maxima. Okay, so we don't need to list it for each one of these curves. We could. Okay, so let's say for the first one, you would say that would be 0, 0 and 4, 0. For the second curve, we would have 4, 0, 4, 2, and so forth. Okay, or you can just make sure that we'll list them all at some point. So I'm going to mark these points 0, 0. We need to take a look at that one. We need to take a look at point 4, 0. Okay, 4, 2 was one of the points that we've already discovered, and then also 0, 2. All right, so once we have all of the points identified, now we're going to evaluate them. Okay, so points that I wrote out, the evaluation for points that I wrote out in green, those are the ones that we found by analyzing the behavior of our function on L1 through L4. Okay, there was a local minima minus the 0.31. Okay, we don't know that yet. And then the ones in blue, those are the corners. Okay, so you can see what I've done here. I evaluated my function at each of these points. Okay, and now what do we do? We just select the maximum and the minimum. Okay, so by inspection, let's see what is the largest value. The largest value is over here. Okay, so f evaluated at 0, 2 is 36. That's going to be our absolute maximum. Okay, and what about the absolute minimum? That's going to be this value right here. That's absolute minimum. Okay, so that's that, and all those other values, they will be local. Okay, but we don't need to be concerned about, because we're only asked to compute the absolute values. All right, so this problem is a good example of why it is important to do an analysis of the function that we're working with on each one of those lines, right, or the curves. So in example 4, we were lucky because we had a very nice symmetric function. Also, we had symmetry of the region. Okay, so we didn't have to do too much work. Some of that stuff was redundant. We could have just, we just said, okay, well, we've done this for x is equal to 2, so it's the same thing as if we redo it for -2, right? But you can see that for this example, that's not going to work. Okay, so I wanted to show you all an example where it is absolutely needed to do a thorough, detailed analysis of the behavior of the function on those line segments. It could be a line segment, it could be a curve of some sort. But yeah, that was the main point of this particular problem. Okay, all right, well, thank you for watching. The next set of videos will discuss Lagrange multiplier method for computing maximum and minimum values of a function when we also have a constraint. So that's going to be the main point. Not only do you have a function, you also have some sort of condition that this function needs to satisfy. All right, thank you for watching, and I'll talk to you next time.